Hello and welcome back, everybody. We are continuing our Chapter 5 on the Newton's laws and forces. And we've been talking about a couple different kinds of forces. We've been talking about the weight force, and we mentioned the normal force already. That is a force that is acting at right angles to a surface. And in many cases, that normal force is what is acting upwards to give us our weight. For example, if I'm standing right here, or there's a ground right there, and I'm a person, and I'm going to be standing right here like that. What gives me my weight is the fact that gravity is acting downwards on me to take my mass and pull it down. We have called that mg. That's your weight force. But if there's no other force to counteract that, then that means that me or whoever this person is would start to accelerate down into the ground. Well, we know that doesn't happen. That the ground or whatever surface you're standing on provides an upwards force that tends to be at right angles to that ground. So it's perpendicular to the ground right there. So we'll call it the normal force. And we've given that the designation of N. Not to be confused with the unit Newton, but the normal force itself we just call N. You can call it Fn if you want. But that's the normal force. So the normal force, in this case, is going to be the same thing as our weight. And so in this scenario right here, you would say the normal force is going to be exactly what our weight is on Earth, because the ground is providing the up force, and it's counteracting the downward force created by gravity, acting on our mass. But we can also have what's called an apparent weight. And this is kind of a more, a more specific application of the normal force. In this scenario right here, the normal force is really the same thing as our weight. But your apparent weight is the weight that you feel, you might say, under your feet. That is the force that you feel, the sense of having weight is what we call the apparent weight. And that means that normal force may be greater or lesser than what it would normally be if you're, I shouldn't use the word normal, than what it would usually be if you're just standing on the ground. So a system can be moving. Like, for example, a great example is an elevator. All right? There's a red elevator right here, and you're standing in there, and of course it's supported by a cable right there. If that elevator is moving up and down, no doubt you've felt this, that your weight, if the elevator is accelerating upwards, your weight, your apparent weight, temporarily feels greater. You feel heavier. Or if the elevator is accelerating downwards, it lurches downwards once you close the door. You kind of feel a little bit lighter. You feel your stomach come up into your gut a little bit because you feel slightly more weightless. Your apparent weight is changing, and it's all a result of you kind of accelerating with or against gravity. So our idea of weightlessness is really having no apparent weight. Now, you can be weightlessness in deep space where there is virtually no gravity at all, or you can be weightless because maybe you're falling through gravity. A skydiver, a person who jumps out of an airplane, all right, and is hurtling towards the ground right there. I should be drawing my motion lines like that, I guess. All right, they're skydiving. They're moving towards the ground. The whole reason they skydive is because it gives them the sense of weightlessness. They're not supported at all. There is no supporting force underneath them, so the bottom of their feet or whatever part of their body it is does not experience any force. So apparent weight, our definition of apparent weight is probably the best way to say it is the supporting force. Whether you're being supported from below or from above, something is holding you up. But if nothing is holding you up, then that would give you the sense of weightlessness. All right. In truth, no object can really be entirely without weight because gravity is an acceleration that basically extends out to infinity. All right. And even if you go out in deep space, there is still microgravity out there. But you can feel very, very close to weightlessness even if you're not exactly at it. So apparent weight is the supporting force. So it's very much like the normal force, but this can actually change depending on what your system is doing. A good example is this next one, example 5.9. So I know this looks like a kind of an odd setup right here, but we have a fish hanging from the ceiling of an elevator, and it's hanging on a scale, like one of those scales that you would see in like a supermarket. Okay, so this fish, this salmon, is 5 kilograms. So we've got a mass. All right, I shouldn't have done that. It's got a mass of 5 kilograms. And so why put it inside of an elevator? Because an elevator is able to accelerate upwards. It's also able to accelerate downwards at various rates. And what that will do is cause the apparent weight of the fish to change. Now, before we get too much into this right here, let's ask ourselves, what is, as the elevator is at rest right now, what is what are the forces that are acting? Oops, I didn't mean to do that. Sorry. Acting on the fish. Well, let's label 1 right now. Okay, we know for sure that the fish, and I'm just going to draw a little point mass right here, has a mass, and this elevator we're assuming is on Earth. All right, so it is affected by the Earth's gravity. So mg, the fish's weight, is going to be pulling downwards. Okay. What is supporting it? Well, it's not being supported from beneath, but it's being supported from above. And that above little line right here, or this hook, is attached to the ceiling, and ultimately, if you go all the way around, the fish is being supported from below. But immediately, it's hung from above. So you could say really the supporting force, it may not be accurate to call it the normal force, but the supporting force might be a better way to put it, is acting upwards. All right, and that force is manifested in, you might say, the tension in that little line right there, or the tension in the hook that hangs from the ceiling. And by the way, one more bit of convenience, this apparatus right here happens to have a force meter built into it. We call that a scale. That's what a scale is. It simply measures force. So whether it's newtons or pounds, it's measuring force right here. So as our system is moving, as the acceleration is upward or downwards, what's going to happen is our scale is going to measure a difference in the supporting force. That is, it's going to measure a difference in the apparent weight. You could call that W apparent as well as another way to put it. Okay, so the supporting force is your apparent weight, and this fish is being supported from above, and we have a way to read the weight on the fish. Okay, let's go ahead and read this. So combining physics and biology at the same time, an instructor asked students to weigh 5 kilogram salmon by hanging it from a fish scale attached to the ceiling of an elevator. All right, so we've established that already. Our salmon is, mass equals 5.0 kilograms. Got it. All right. What we're being asked to find is, what is the apparent weight? Actually, for two, we're going to do A and B together. All right. A and B, the apparent weight if the elevator is accelerating upwards at 2.5 meters per second. Okay, or per second squared. So for A, the acceleration for part A equals 2.5 meters per second squared, and I'm just going to leave it like that because it being positive, that's going to assume upwards. Okay, and by the way, let's just go ahead and establish that we're going to call upwards positive, and downwards is going to be negative. Okay, the acceleration for part B, right here is going to be 3.2 meters per second squared, but it's going to be downwards, and so it's going to be a negative 3.2 meters per second squared. I'm sorry, I got that wrong. This is the acceleration for part B. This is acceleration for part C. And the initial for part A, the acceleration, in fact, I'm going to erase all of this. Well, no, I'm not. I'm going to write at the top right here. The acceleration for part A is 0, right? How do we know that? Because we're told that the fish is at rest. All right, there's a lot of letters right here. Let's just do, in this segment, let's just do at rest for now. Okay? And then in a separate segment, we're going to move on to part B, C, and then D. Okay? So you might say for D, part D, the fish is weightless. All right? So we're going to say that the supporting force on the fish, or you might say the apparent weight, is 0. That's what we're establishing. Okay? So I'm going to take all this and just sort of shrink it down. And we're going to do part A in this segment, and then we're going to do parts B, C, and D in a subsequent segment. Okay? So I'm going to shrink that like that. So, for part A, what is the apparent, I'm going to call it F sup, or I can't even write right here. The force supporting, also known as the weight apparent, whatever it is what? That's what we want to find, okay? So, let's draw a fish right here, okay? We just have a little fish guy like that. And so the supporting force is going to be upwards, and that's what we're calculating, all right? The downwards force is going to be mg, right? Mass times gravity. So these are our forces that are acting on this fish. So we can actually write a statement about the net force on the fish by saying this. Net force on the fish, and the salmon, is going to be what? Well, it's going to be our supporting force minus mg, right? Because mg is acting in the negative direction. Supporting force is acting upwards. This is a statement, you might say, this is the component statement we can make about all the forces acting on the fish. This is what we're solving for, by the way. All right? But what is the other way we can state the net force on the fish? I don't want to write that in red, write it in blue. Net force on the fish is what? It's always going to be mass times the acceleration of, you might say, the fish, okay, or the system that the fish is connected to. All right? These both these things being equal, we can say, all right, we can set this equal to that. So I'm going to move down here and say, all right, the supporting force minus mg, right? Minus mg is going to be equal to, oops, I meant to change the blue. It's going to be equal to the mass times acceleration of the fish. All right? Mass times acceleration of the fish. All right? Now, you're probably going to see what this is going to turn out to be, but this is mathematically proving that the supporting force is going to be what it is. Now, remember, what is the acceleration of the fish? In part A, the acceleration of the fish is 0. It's going to be 0 meters per second. So that should give you an idea of how this is going to shake out, but let's just go ahead and solve for the supporting force on the fish, which is going to be really the apparent weight. Okay? So down here, the supporting force, I'm getting tired of switching to red for the mg. I'm just going to write it in blue. Is going to be what? Well, we're going to take that mg and subtract it. Oh, I'm sorry, it's being subtracted, so we're going to add it to the other side, right? It's going to be mass times the acceleration of the fish plus mg. All right, now we just got done saying that the acceleration of the fish is 0. So that's going to go away. And so your supporting force, or you might say the apparent weight, both of those are perfectly good ways to say it, is going to be equal to 5 kilograms, the mass of the fish, times acceleration of gravity, 9.81 meters per second squared. And what's that going to be? 9.81 times 5.0 is 49.05. I'm going to round that to 49.1 meters. Oops. Not meters per second. Newtons, right? Newtons. And that is what the scale is going to register. That's what the fish weighs, you might say, when it's at rest. When you're just weighing it in the supermarket, or when you're just at a in a system that is at rest. We're going to find out in parts B, C, and D that this fish is going to weigh less if we accelerate the elevator upwards, downwards, and we're going to see how we have to accelerate it in order for it to weigh nothing at all, or to appear to weigh nothing at all. So, but for now, I'm going to give you a break, and I'm going to stop here. I'm going to pick up on the next one. So thanks for following along. Make sure you ask me if you have any questions, and I'll see you on the next one.